Hey kids, just want to make a video here because I thought my lesson yesterday was crappy. So now I'm going to make a video. Alright, so entropy. What is entropy? Entropy is denoted with capital S, and it's defined as the disorder in a system. The greater the disorder, the greater the entropy. So if we look at the different phases of matter, solids have less entropy than liquids because in a solid, all of the particles that make up that solid are locked in place. They're unable to move in relation to one another. So we could say that a solid is a very ordered state. If we melt that solid, now the particles are free to move about, so they can mix and match. That means a liquid has more disorder. If we take that liquid and boil it, now the particles are moving faster, they're all spread out, zipping to and fro. So as we go from solid to liquid to gas, we see entropy or disorder increasing. Another way to look at this is if we have a sample of sand. If I arrange that sand into a sandcastle and then break the sandcastle so it's just a pile, we would say that the sandcastle was more ordered than the pile. So a pile of sand will have greater entropy than the castle itself. Okay, so entropy is disorder. So there's a few different factors that can influence entropy. One of them is the number of particles. More particles means more entropy. Think about this like a highway. If there are more cars on the highway, we would say that the highway is more disordered than, say, an empty highway. More particles means more disorder. Like we looked at on the previous slide, we could also talk about the phase. Gas will have greater entropy than liquid or solid. Aqueous, something dissolved in water, will also have a greater entropy than solid, right? So we have to look at the phase. And finally, the available energy of the particles, temperature. So if a reaction is highly exothermic, releases a lot of heat, that can actually lead to an increase in entropy because when we heat things up, when we increase their temperature by adding heat, they begin to move faster, right? And we know that faster moving particles will be more disordered than slower moving particles, just like faster moving cars, you could say, is a more disordered state than slower moving cars. You're going to get more collisions and things because of that disordered state. So those three things are things we're going to look at when we're determining whether entropy increases or decreases in a chemical reaction. If entropy increases, then the sign for the change in entropy, or delta S, would be positive. If the total entropy decreases as a result of the reaction, then the sign of delta S would be negative. All right, so let's look at some examples. In the first example, I have all gaseous reactants and products. Everything is in the gas phase. So I can't really use the state of matter to determine whether or not the delta S is positive or negative, but I can use the number of particles. On the reactant side, I have 1 mole of nitrogen and 3 moles of hydrogen for a combined total of 4 moles. On the product side, I only have 2 moles of gas. So because I have more reactants than I have products, that tells me that delta S here will be negative because we're going from many to fewer. In the next example, I have liquid water going to gaseous water. Now we know that gases will have a higher entropy than liquids. So if we're going from liquid to gas, then delta S must be positive because entropy is increasing. The final example, we have solid calcium carbonate decomposing into solid calcium oxide and carbon dioxide gas. So there's two things we can consider here. One, we're changing the state of the reactant from solid to a gaseous product, so that would represent an increase in entropy. We're also going from one particle on the reactant side to 2 on the product side. So in addition to changing to a state that contains more entropy, we're also increasing the number of particles, so that means delta S would be positive. All right, so of course you're going to be asked to calculate delta S. Now the only source we have that gives us data on entropy is Table 12 in the data booklet. And Table 12, we've previously looked at Table 12, and Table 12 we learned gives us enthalpy of formation, or delta H with a subscript of F. That table also contains entropy values, or S values. So when we calculate delta H using Table 12, or enthalpy of formation data, we took the sum of the enthalpies of formation of the products and subtracted away the sum of the enthalpies of formation of the reactants. So delta H was products minus reactants. Whenever we're using Table 12, we're always going to use the same method. So when we calculate delta H, it's just going to be, or delta S, excuse me, it's going to be the sum of all the entropy values for the products minus the sum of all the entropy values for the reactants. So one important thing to note about using delta S in calculations, if you look at the headings in Table 12, you'll see that delta S, or entropy, has a unit of joules per mole Kelvin. But if you look at delta H and delta G, which we'll talk about, you'll see that they have units of kilojoules per mole. Whenever we're doing mathematical calculations, it's really important, as you guys know, that we got to tweak our numbers in such a way to make it so that all of the numbers have consistent units. Only kilojoules will cancel kilojoules. So whenever we're working with entropy, if we're combining it with delta H and or delta G, we have to make sure that we divide by 1,000 to convert joules into kilojoules. All right, so let's talk about thermodynamic favorability. So as it turns out, the universe has certain desires. We call those desires the laws of physics. But I like to think in terms of what the universe wants. Everything in the universe, according to the laws of physics, will tend towards stability and disorder. For the disorder example, imagine that I just keel over and die. Now, while I'm alive, my body is fighting against that disorder. But once I die, the fight stops and nature takes over. Over time, assuming I'm not preserved in some way, my body will decompose. It'll go from the mega-ordered state that it is in now and kind of become a pile of gases and brown goo. Okay? I would naturally become less ordered over time because that is the drive of the universe. So which type of reactions lead to more stable products? Well, remember, exothermic reactions lead to more stable products because the products contain less energy than the reactants. So any reaction that has a negative value for delta H is thermodynamically favorable. The universe also will tend toward an increase in entropy, more disorder. So any reaction where delta S is positive will tell you that the universe is in league with what's happening in that reaction. All right, so now let's talk about spontaneity. A spontaneous reaction is a reaction that will just occur naturally. It doesn't really need any kind of force to run. It'll just happen over time. Now that does not mean it'll happen quickly, it just will happen. And we'll talk about the rate of chemical reactions in Unit 6. Now, one example of a spontaneous reaction is the decomposition of hydrogen peroxide into water and oxygen gas. This process is a spontaneous process. Most people have hydrogen peroxide at home. You use it as a disinfectant when you get a cut or a scrape. We don't get a lot of cuts and scrapes once we enter the age of maturity. So sometimes that hydrogen peroxide has a tendency to sit in the cupboard under the sink in the bathroom for years and years. Sometimes when we open that bottle of hydrogen peroxide, you'll hear a little tsh, because while it was sitting there, this process was happening. And oxygen gas was created over that time. So when you take the cap off, that's the oxygen escaping. So spontaneous just means a reaction will occur under certain conditions. So to determine whether a reaction is spontaneous or not, we use something called Gibbs free energy. Gibbs free energy is denoted with a capital G. Gibbs free energy can also be found in Table 12 of the data booklet. So when we're calculating delta G, you can also use the products minus reactants method to do so. As it turns out, if the sign of delta G is negative, that means that the reaction is spontaneous. If delta G is positive, that means it is a non-spontaneous reaction. So as it turns out, the combination of delta H and delta S and whether or not they are positive or negative can actually determine whether or not a reaction is spontaneous. So let's go have a look. We're going to talk in each case for 4 reactions. You can see each one has a different combination of positives and negatives. We're going to determine whether delta S and delta G, or delta S and delta H, are thermodynamically favorable. Look at how the signs will affect our equation up here and determine whether or not the reaction will be spontaneous. So the equation that's used to calculate spontaneity is delta G equals delta H minus T delta S, where T is the temperature in Kelvin. So when I look at reaction 1, I see a negative value for delta H. That means delta H is thermodynamically favorable because the universe prefers delta H as negative. Delta S is positive, which is also thermodynamically favorable. Well, let's look at the signs. If delta H were negative and delta S were positive, because we're subtracting away here, temperature in Kelvin will always be positive. So when we plug our values, negative and positive, into this equation, delta G will always be negative. So if your delta G and delta H and delta S values are in league with the universe, then the reaction will always be spontaneous. So we'll say always yes. Now let's look at reaction 2. In this case, our delta H is positive, which is unfavorable. Our delta S is negative, which is also unfavorable. If the sign of delta H is positive and the sign of delta S is negative, when we plug the values in, we'll be subtracting by a negative. So this will become positive. T delta S, will become positive. So if delta H is positive, that means delta G will always be positive. And when a reaction where we're going against the universe will always be non-spontaneous. Now let's look at reactions 3 and 4. Before I do that, I'm going to pause the video to make sure that I'm not missing class. I've got 20 minutes before class, so we good. All right, so for reaction 3, delta H is positive. That's unfavorable. Oops. But the delta S value being positive is favorable. So let's look at our equation. Erase all this junk up here to make it nice and neat. It's not working. Okay, so we'll just do the best we can. If delta H is positive and delta S is also positive, then the sign of delta G will depend on the magnitude of T delta S. If T delta S is greater than delta H, that means delta G would be negative. If T delta S is smaller than delta H, then delta G would be positive. So we'd say here that it really depends on temperature. Now let's think about a type of reaction where delta H and delta S are both positive. The thing I like to think about or to use as an example when explaining this is water, the freezing of water or the boiling of water. So let's consider the boiling of water. Boiling water is indeed endothermic. You have to put energy into water to make it boil. That's why we put pots of water on the stove to get them boiling. Boiling water also goes from liquid to gas, so it would have a positive change in entropy. At which temperatures is boiling water a spontaneous process? At low temperature or at high temperature? Well, of course, water will only boil if you put it at high temperature. And the same thing applies here. Any reaction that has positive values for both delta H and delta S will only be spontaneous at high temperatures. Now let's look at reaction 4. Now instead of both positives, we have both negatives. So this process is going to kind of be like freezing water. Freezing water is an exothermic process, and going from liquid to solid represents a decrease in entropy. So our delta H value here is favorable, but our delta S value is not. So now let's change these signs. Let's see if I can do it now. I don't know if I'll be able to. I can't. I'm sorry. I'm trying my best. We're back to school. So instead of being positive, now these are both going to be negative. Now we're going to be subtracting a negative value. So if T delta S is larger than delta H, that means delta S or delta G would be positive. So T delta S has to be smaller than delta H in this case in order to come out with a negative value. That means that in this case, delta G also depends on temperature, and delta G will only be negative when T delta S factor is small. So the temperature also has to be low. So reactions where delta H and delta S are both negative will only be spontaneous at low temperature. It's kind of easy to remember that, because when I think of positive, I think of high, and when I think of negative, I think of low, right? But just know that the signs of delta H and delta S can determine whether a reaction will be spontaneous. And let's look at a few examples of this. So the first example I have here is the combustion of methane. I know that for the combustion of methane, delta H is negative because this is a combustion reaction, and combustion is always exothermic. Now for delta S, it can be a little bit tough to tell here because we have equal particles on both sides. I have 3 total moles of reactants and 3 total moles of products, and they're all the same phase. But I can tell you that delta S for combustion will also be positive. Think about the amount of heat that's added. CO2 and water, steam, will have more energy, more thermal energy than the reactants because the reaction is producing a lot of heat. Okay, so that's that third factor we have to consider. Well, delta H negative and delta S positive is with the universe, so combustion is spontaneous. Now, a lot of people think spontaneous, like it just bursts into flame. Of course not. You have to get the fire started, but all we're doing there is satisfying the activation energy. Every reaction in the universe has activation energy associated with it. In the next example, we have hydrated barium hydroxide reacting with ammonium nitrate in a double replacement reaction. Now, one thing I can tell you for this process is that delta H is indeed positive. This is an endothermic reaction. But I see here that I have 3 moles of reactants and 10 moles of products, so entropy is most definitely increasing. Well, this reaction will only occur spontaneously at higher temperatures because delta H and delta S are both positive. Next example, we have the water going from solid to liquid, water melting. We know in that case, delta H is positive. It takes energy to melt ice. And delta S is also positive. Well, when does ice spontaneously melt? At higher temperatures. The next example is liquid water going to solid, so freezing. In this case, delta H is negative because freezing is exothermic. And delta S is also negative because we're going from liquid to solid. If they're both negative, that means that the reaction is only spontaneous at low temperature. Well, when does water freeze? At low temperatures. And finally, the last example is the dissolution of calcium chloride. So this dissolution, some of you probably know, I'll give you a hint, calcium chloride is what's used to melt ice on the roads. So this is an exothermic dissolution. We're also showing here an increase in entropy because we're going from 1 mole of particles to 3 moles of particles in the product side. So because both of these factors are in league with what the universe wants, they're thermodynamically favorable, this process will always be spontaneous. All right, I'm going to end the discussion here because I have to get to class, and we're already 22 minutes in. Hopefully this was more clear than the lesson in class. I know it was. If anybody has any questions, of course, you can bring them to class. And thank you so much for watching. Don't forget to like and subscribe.